In this video, the basic concept of power system stability will be discussed. Systems are very complex with a huge interconnected network of transmission lines linking generators and loads. Successful operation of power system depends largely on the ability to provide a reliable and uninterrupted service to the loads. So the power system stability assessment is a very important concept in today's power systems. The IEEE task force has given a definition of power system stability as an ability of a electric power system for a given initial operating conditions to regain a state of operating equilibrium after being subjected to a physical disturbance, with most of the system variables bounded so that practically the entire system remains intact. The power system is subjected to a wide range of disturbance. The magnitude of disturbance may be small and large. For example, there may be a sudden load change or there may be generation changes. The network changes because of the outage of a transmission line or an outage of an equipment leading to the change of the configuration of the system. So during all these situations which occurs on a power system, the object is that all the variables of the power system should remain bounded, that it should remain within their technical limits. As we have already seen before that the voltage bus of each of the system has to be within the limits. The real and reactive power output of the generator is also to remain within bounds of minimum and maximum limits, and also there are limits of the power flow through the transmission line. As shown in this figure, it is seen that there is a power flow limit through the transmission line, because the transmission line has a capacity of it for the power flow over it. Similarly, the bus voltage is having a power flow limits and the generators is having a power flow limit, which we are also calling as the inequality constraints. So the system, when subjected to all the type of disturbances which are occurring on it, and it is able to regain back the operating equilibrium or the steady state situation, we'll call the system as stable. This figure shows the power system stability and its classification, that is the different type of stability issues which occur on a power system. The power system stability can be broadly categorized into three sections as rotor angle stability, frequency stability and voltage stability. Rotor angle stability refers to the ability of synchronous machine of an interconnected power system to remain in synchronism after being subjected to a disturbance. It will depend upon the ability to maintain or to restore the equilibrium between the electromagnetic torque and mechanical torque of each of the synchronous machine of the system. The equilibrium between the two torques is disturbed, then it will result in the form of increasing or decreasing acceleration of the generators with respect to the other generator, leading to the loss of synchronism of the system. The other power system stability issue is voltage stability, which refers to the ability of a power system to maintain steady state voltages at all the buses after being subjected to a disturbance from a given initial operating condition. Voltage instability may occur in the form of progressive rise or fall of voltage at some of the buses. You might have heard of the term voltage collapse, which means a sequence of events accompanying the voltage instability leading to blackout or abnormally low voltages in significant part of the power system. The third type is frequency stability, which is the ability of power system to maintain steady state frequency following a severe system upset resulting in significant imbalance between the generation and load. Now if we look at the three issues, we can see here that the three variables are involved here: rotor angle delta, frequency and the voltage. All the three variables should remain within their specified limits, which you can also call as the technical constraints or the inequality constraints on the system. The three stability phenomena has been further classified as the small disturbance and large disturbance, that is in terms of the magnitude of disturbance that is occurring on the system. For example, if you look at the rotor angle stability, it has been subcategorized as small disturbance angle stability and large disturbance angle stability, also known as transient stability. Small disturbance rotor angle stability is concerned with the ability of the power system to maintain synchronism under small disturbances. The disturbances are so small that the linearization of system equations is possible. In the large disturbance rotor angle stability, also known as transient stability, it is referred as the ability of power system to maintain synchronism when subjected to a very large disturbance or a severe disturbance, such as a short circuit on a transmission line. That is a three-phase fault also, you can say. In such a situation, the resulting system response will involve large excursion of the rotor angles, and this will lead to the non-linear power angle relationships. Similar subcategorization of the voltage stability has also been done in terms of the small disturbance and large disturbance voltage stability. Also, from the time frame of interest, the different stability issues has been further subcategorized as short term and long term, where the time frame is of interest. For example, for transient stability, the time frame of interest is that we must be able to identify this problem within 3 to 5 seconds following a disturbance. The stability problem is concerned with the behavior of the synchronous machines after a disturbance. For convenience of analysis, stability problems are generally divided into two major categories: steady state stability and transient stability. Steady state stability refers to the ability of power system to regain synchronism after small and slow disturbances such as gradual power changes. An extension of steady state stability is also known as dynamic stability. The dynamic stability is concerned with small disturbances lasting for a long time. Transient stability study deals with the effects of large sudden disturbances such as occurrence of a fault, three-phase fault particularly, the sudden outage of a line, or the sudden application or removal of load or tripping of a heavily loaded line. Such studies are conducted when new generating and transmitting facilities are planned. These studies are helpful in determining the nature of the relaying system needed, critical clearing time for the circuit breakers, the voltage level of and the transfer capability between systems.